Well, we're ready for Class C, which is Special Relativity. And we'll look at this marvelous area of physics, and we'll show you an innovative way to derive the Lorentz Transformation using the rotation matrix. And the secret there will be is to know what doesn't change when you make a rotation. It's the length of that distance, or that length from the origin to a point P. And by setting it up that way, we will show the Lorentz transformation, a derivation. And we'll talk about Lorentz contraction, time dilation, and derive the famous equation E equals mc squared. So it's a cool class on relativity, showing the emphasis of a theoretical approach to see like the holistic, the kind of whole picture of relativity. Relativity, Einstein wanted to call it like the invariant theory, I believe, the invariant theory, a theory of invariance or absolutes, because the two postulates, one that said that the laws of physics are the same in all frames of reference that are moving with constant speed. That's your inertial frame. And then he generalizes later to the general theory of relativity, which has acceleration in 1915. But this is 1905 here. And then the second postulate that from all frames of reference in the inertial frames, the speed of light is measured to be the same. So these are absolutes. Unfortunately, folks that don't study these things in detail take the relativity to be relative, like subjective, which is, well, that's true for space and time. See, space and time are going to be relative, but it doesn't mean everything's relative, and that can be easily misunderstood. When I team taught humanities with colleagues, had to be careful there. And it was good actually to have a physicist involved with that, because when they talked about the 20th century and the center does not hold, they talk about the Yates and talk about traditional things kind of falling apart, and then they bring in physics and say physics falling apart, here Newtonian physics. Well, that's true, Newtonian physics did have difficulties, but it wasn't replaced by relativity. It was replaced by new invariances, new absolutes. So just bear that in mind if you ever run across something in the humanities where they're overemphasizing the relativity and not emphasizing the true nature of the theory, which is to find what it doesn't change. And you don't have to go past the two laws to understand that. The first law, all the laws of physics have to be the same. That means if you play baseball or soccer or football in a moving frame that's not accelerating, that you would play the same way. Everything would be the same. Your weight would be the same. Your measurements would be the same. Now, if you accelerate, that'd be different, but we're not talking about those frames. So all the laws of physics would be the same. You couldn't tell that you're moving. And then the second postulate, that the speed of light is constant in all frames of reference, which is interesting, that we'll see later the speed of light can be related to constants in electricity and magnetism, electromagnetic waves. So that's another topic we'll look at later. And we'll have a little bit of fun with four vectors, to look at the four-dimensional aspect of the world, where we have X, Y, and Z, spatial, and then we have T for time, and we put C in front of the T to make it have the same dimensions as space, and has some neat equations with the four-dimensional world. I hope you enjoy the relativity class. Chapter C, Relativity. C1, the Galilean Transformation. The Galilean Transformation is a common sense, basic Newtonian kind of way of thinking that will have limitations. Now here's how it goes. You have a frame of reference, we'll call K, which is stationary. We're with this one. And then there's another one that's moving to the right. That's constant speed v. And we say that at, let's say this frame, we're looking at x axis. This is an x prime axis, so this frame is the prime frame, and this would have a time t associated with it, and this would have a time t prime associated with it, like a clock in this frame, t prime, and a clock in that frame, be t. And let's look at a point here. Now this point can be described by x prime as measured from the origin. Now we're assuming here that when x equals x prime, that's at t prime equals 0. So they started out with the origins coinciding when they start their clocks. Then this distance here would be the velocity times time. We're in this frame watching this other frame go by, so in time t, this frame is down the road a bit. And then if we go from this point way to the beginning, that would be the x, looking at the x coordinate. So therefore we have the equation x is vt plus x prime, which we can write as the prime one first as a dictionary to go from xt to x prime in this fashion. And t prime, since time is considered absolute, we have these are the equations for the transformation, and that's the Galilean transformation. And if you looked at, for example, a velocity, delta x prime over delta t prime, you would have a delta x, and since the delta t prime is the same, we could do that, minus v delta t over delta t. So we just take deltas here and divide by delta t prime, which is the same as delta t. Then you get the velocity in this frame that's moving is this velocity. We'll call these u so we don't get confused, minus v. So if I write that as u as v plus u prime, that's saying that this frame that's moving, if this thing is moving at some speed in this frame, but the entire frame is moving at v, then we would see the total. Let's say if there's some kind of like a boat here, and there's some car going u prime on the boat that's going v, then we would see here a velocity u prime plus v, or just add them two together. That's common sense. That kind of makes sense, but we'll see that this is not going to be valid for very fast speeds. All right. That's going to break down. So if we have our graph again that we had earlier, where we had the speed along the vertical, and we had the size along this direction. And let's just divide this into regions. So this is fast, and this is slow, and this is large, and this is small. This is classical physics, F equals ma, and that's where this applies. What we just did would be in here. Here we're going to see that this speed of light constant is going to be a constant c, so I'll just write this equation here to be the same in all frames of reference, which we'll be discussing shortly. And then here you could write down the de Broglie relation at the wavelength is related to momentum. So like particles have wavelengths, and then this is Dirac. So we want to study this area. Notice that modern physics, what's considered modern physics in the curriculum, physics majors, is this x is c times t, which is going to be the same in all the reference frames. And we'll put the de Broglie relation here. In other words, modern physics are these two areas here. C2, the Lorentz transformation, when they were doing experiments, say I guess the main one, Michelson-Morley experiment, and they were finding that the speed of light was doing things that they hadn't expected. Like, in other words, this Galilean stuff wasn't working. That Lorentz came up with a transformation that did fit the data here, and we're going to look at this transformation in a second. We're going to see where this comes from. Einstein, with the idea of special relativity, can derive these. So, but these were known before Einstein by Lorentz, that if you have this kind of strange transformation going on, you could describe the data. The data would be consistent with this idea. So let's go on to do C3, special relativity. And in special relativity, that brings us to Einstein. And the two postulates of relativity, the first postulate is that the laws of physics are the same in all inertial frames. And the second one is that the speed of light in vacuum is the same in all inertial frames. So these are the two postulates of relativity. We can just summarize for the first one, laws of physics, saying, now the frames of reference that he's looking at are called inertial frames, and the inertial frames are those where you have the constant v, a constant speed. There, we can actually put a vector sign on there since direction won't change either. And the general theory considers acceleration. That's 1915, so we're looking here at 1905, all right, in this case. The second postulate would be that the speed of light, the light speed as observed from these frames, c is a constant. And that's going to play havoc with the Galilean transformation, because if you then have the boat and you have, say, a flashlight going like this, speed c, and this boat's going at v, then you're going to see in this other frame, say, it's going to be the speed of light c also. So in other words, c equals c. What are you saying here? But that is what we're saying. We're saying that if you have these two frames, the k and the k prime frame, and this one's going at speed v, we're saying that here, if light should be emitted, say when t equals t prime equals 0, you know, x equals x prime equals 0, so light is emitted at the origin, and then the light will travel in both frames. But what we're saying here is that the speed will be the same in each frame. So in other words, the speed of light is c is a constant from either frame. So this is the x t variables, and this has the x prime t prime variables. So to account for light traveling in either direction, we'll go ahead and square this so that plus or minus x gives the same result. And we get this equals c squared t prime squared. And then we'll subtract the right-hand side, so we can get 0. So that would be then 0. And if we subtract the right-hand side here, we would get 0 again. So this would be what's the same. Notice, by the way, that relativity is kind of a bad term for this theory. And remember, when we talk about theory, we mean body of knowledge. Because, see, the laws of physics are the same in all the frames of reference. That's like an absolute. And the speed of light is constant as an absolute. So really, it's more like a theory of absolutes. But we're going to find that time and space get subjective or get relative to make these two things work. So that's why the terminology they evolved, that was relativity. But Einstein really want to call this like a invariante or something like the invariant theory of absolutes would be like better. So we just discover here that space and time are not absolutes, but something else is, like the laws of physics and the speed of light, and then space and time are relative. So just bear in mind, a lot of folks, there's a danger in the humanities to refer to relativity as, a subjective sort of thing with the X's and the T's and, being different, but really it's an absolute kind of thing, looking for the invariance, things that are constant. But now, our rotation matrix will come to help us. If we look at, say, X and Y, and then we rotate to get some Y prime and X prime, what's invariant here is this distance from the origin to point P. This length will be the same, even though the X and X prime, you can write this as having an X this way. This is your X axis, and this is your Y axis, the axis, and here's your X, here's your Y, and then this would be your Y prime, and then your X prime would be there. But you can have your choice. You're going to find that X squared plus Y squared will equal X prime squared plus Y prime squared. In other words, the invariant is the length, the distance from, say, center of town to this house. But you can use coordinates of your choice. You'll still agree that the distance is a constant. It's the same. It's invariant. So that's the invariant. The invariant would be the distance, or the distance squared. Now we do a trick. Due to Minkowski, we're going to let Y, and we probably here with this Y just should emphasize that this Y is going to now become a time, ICT. So this Y axis is not going to be a traditional distance measurement like X. It's going to be a time variable. So therefore Y prime is ICT prime. And then when you apply that by this formula here, where you're going to square things, you'll see that you'll get X squared, and then squaring the Y is minus C squared T squared. And then this would be X prime squared. And then when you square the Y, you get the Y prime, you get this. So in other words, this is the invariance that is important to special relativity. Like, this is going to be capturing the essence. But we know how to transform these coordinates because we have done this before. In other words, X prime is equal to X cosine theta plus Y sine theta, where the angle of the rotation is theta. And here, Y prime would be minus X. This is from our other class, all right? We're just writing down the rotation matrix. So this is the Lorentz transformation if we can get rid of the theta in terms of the velocity. So if to express the theta in terms of velocity, what we're going to do is we're going to look in the K prime frame, and we're going to have delta X prime to be 0. In other words, have that point stationary. Let's pretend look at that point being stationary, then its velocity will be v, because the frame is moving. This frame is moving at velocity v. So then we come here and say delta x prime, which is the delta x times the cosine of theta. And here, this is IC delta t, all right, because remember that the y is the ICT. And this is going to be 0. And if that's 0, then we can write down delta x cosine theta equals a minus IC delta t sine theta. Okay, this is, since this equals 0, let's go ahead and subtract 1 from each side. And then delta x over delta t, see, that's going to be your velocity. That's going to be v. That's going to be equal to minus IC. When you divide by delta t, you'll have the delta t go away, and we're going to divide by the cosine, so we would have this. So we get the 2 steps. We divide here both sides by delta t and cosine theta. And that gets us then delta x over delta t equals minus IC sine theta over cosine theta. So this is the v. So this is the tangent. So this is basically saying that the tangent of theta, this is minus IC times the tangent of theta. So the tangent of theta is equal to minus v over IC, all right, just by dividing by the minus IC. And if we multiply top and bottom by I, we would get I v over c, since I times I is negative 1. Now, this is crazy. How can you have a tangent equal to imaginary number? Something like that's kind of weird. So what we're going to do here is not let this phase us. This is things that, like, similar to what Feynman would do later in history, where when we would do mathematical manipulations, get strange things like this. He would just plow ahead and not worry about it. So here, we make the triangle with the angle theta, and for the tangent, just put I v over c and put the 1 there. So that does have the tangent, the one we want. And for the transformation, if you look at the transformation, x prime is x cosine of theta plus y, which is the ICT sine of theta. So the Lorentz transformation is just putting in cosine sine. But what is this hypotenuse here? Well, if you take square of this, you get 1. If you square this, you get minus v squared over c squared. Take the square root. This hypotenuse. The hypotenuse is going to be the Pythagorean Theorem. You're going to look at 1 squared, plus this squared, and take the square root. But when you square that, you get the minus v squared over c squared. And that means for the cosine here, your cosine is going to be 1 over the hypotenuse. And for the sine, you'll have I v over c over the hypotenuse. And that would get us here, this would be x. You have the same denominator here, so we can go ahead and do this. And I times I is a negative 1, the c's cancel, so this is minus vt, so that's the transformation. Now earlier, we had x prime is x minus vt, that was Galileo, or the Galilean. And notice that if the velocity is very, very small, then you can neglect this, and actually you would get that. That's that correspondence principle we talked about. And then for the other case, since the y prime is minus x sine of theta plus y cosine theta, this is your IC t prime. This is minus x. And then for your sine, we just do the same thing, IV over c over the square root. And then this is ICT, and for the cosine, just have the square root. Putting in, this in for the cosine, but now it's multiplying by the y, so ICT times that. And over here, the sine is there, and there's the minus x. So here you could divide by the I, and you divide by the c, so you would have t prime is equal to, and if you divide by IC, then this t will be by itself, and I'll write that one first. And then if I divide by the I, this will go away, but I'll have a c squared. There'll be a minus sign, so minus x v over c squared over the square root. And that completes the Lorentz transformation. So we have the two equations. So that second term, just be careful, IC goes away. Well, that's the first term, IC goes away. But for the second term, you have the minus sign, you have the x, and the I will drop out. You'll have the V, and the C will be squared when you divide. And that's the Lorentz transformation. So that's what Lorentz had discovered to work. Okay. This derivation, by the way, I want to give credit. I learned about this trick in this reference here. The cool derivation was in Landau and Lifshitz, the classical theory of fields. This date back to a series of books written by Russian scientists, theoretical physicists. Very, very nice. C4, space and time. Now, two famous things about relativity is the Lorentz contraction and the time dilation. So if you have a frame of reference here, that's, say, call that the lab frame, that's where we are, and then we're watching a frame that's moving by, velocity v, and there's a ruler in here that has a certain length, say L naught. Then what we're going to do is we're going to look at what that length looks like from the other frame of reference if we were to simultaneously make a measurement, at the same time, the beginning and at the end. So we have our Lorentz transformation that we already derived, which is this formula here. And if we take delta x prime, that'll be delta x minus v delta t over 1 minus v squared t squared. Now, to take the measurement at the exact time from the lab, as we're looking at this thing moving by, this will be 0. This will be the length of the ruler in the moving frame, and this will be the length of the ruler that I measure. And you can see by rearrangement here that the length is contracted. Since the velocity over c is less than 1, you're going to have then a contraction. So that's the Lorentz contraction formula. It's called Lorentz contraction, and that's very nice. Then for time dilation, okay, that one here, this is the Lorentz contraction. And then for time dilation, we're looking at a clock. So you have the K frame, you have the K prime frame, you put a clock is in the moving frame. So there's this clock, and that's the T, that's clicking away at the T prime. And what we would like is that clock not to move in that frame. So that means we need to have the delta x prime to be equal to 0. So what I'm really interested in is I'm looking at the ticking of the clock in this frame, delta t prime, and the clicking of the clock in my frame. I want this to be 0. So really I want to solve for the delta t, But over on this side, I need to have delta a t prime and delta x prime. And the problem here is that when I write down the equation that we derived earlier, this one here, okay, this one has the prime one equal to the other stuff. I really want this one to be mine, t, so I can make the measurement. So a nice trick is, if you want to do the switch, you can just let v be minus v. So if v's going the other way, that would be the easiest way to make this transformation, because from the point of view of this frame, this one's going to the left. So that means we could write t is t prime plus x prime v over c squared, 1 minus v squared over c squared. So that's how I can do the switch. Now, it's probably not a bad idea once in your life, maybe when you study relativity in your modern physics course, to actually take the equations, these two equations here, and just solve for x and t, just like do it the long way. And if you do this the long way, you will get, this answer. And if you do it the long way, you will get, for example, the x would be the x prime plus vt prime, like this. So you would just like switch the v sign and like switch the prime. So it's not a bad idea to do that once in your life. All right, so that's how you can get this relation very, very quickly. So then I want the delta t is delta t prime, and then this delta x prime is going to be 0. So since delta x prime is 0, the clock stays where it is in its moving frame, then you have your answer. If you want, you could put down plus the delta x prime, the v over c squared, and have all the steps shown, and then just say this thing is 0. This is the time I measure in the lab frame. This is the time of the moving clock. It's in its own frame. It's called the proper time. And you can see that now the time is stretched because you're dividing by something that's less than 1. And that is the time dilation formula, the famous formula. Okay, now we move on to C5, which is velocity addition, and we're going to show here that if you're on a boat, say, moving at speed v, and there's some car here moving at speed u prime, because that's the k prime frame, the one that's moving, then we're going to show that the speed as observed from the water here in the lab frame is not going to be equal to u prime plus v, which is what we found with Galileo. Okay, so what we do here is we do the same thing as we did with Galileo. We just took the deltas. So we're going to do the same thing here. We have x prime is v minus, x prime is x prime is x minus vt. And, sometimes people just get tired of writing down this thing, but the gamma, this definition, 1 over v squared over c squared, that's a definition. So that's the x prime, and then the t prime would be t minus x v over c squared, and a gamma. So what we want to do is take delta x prime and divide by delta t prime, and that's going to be the velocity in the moving frame, the u prime. So if we do that, we get delta x minus v delta t, and here, see, gammas are going to cancel when you do this, and this is delta t minus x over c squared delta x rather times v. So I think we have it here, delta t minus delta x times v over c squared, and then delta x, and then a delta t. Now if I divide top and bottom by delta t's, I'll have delta x over delta t minus v, and this is 1 minus delta x over delta t v over c squared. So I'm showing that u prime is equal to u minus v, which is kind of what we had before for Galileo, but now we have other stuff. We're dividing by 1 minus u v over c squared. Okay, but now if we want to have u on the right hand side, we could do the trick we were talked about earlier. We can simply change prime and unprimes and just flip the v. So that would be a u prime plus v over 1 plus u prime v over c squared. And I do recommend once in your life to do it the long way. In other words, go ahead and solve this for u the long way. Maybe we can just do it. Let's see, u prime minus u prime v over c squared is u minus v. And I would have here u prime plus v is then u1 plus here the u prime v over c squared. I just couldn't resist just doing it for you here. So like we just did it. It's like, so we just did it the long way. All right, so that's it. And that's showing that if you have then, see the boat going at V, or maybe a rocket ship, say, and then here's a flashlight sending out speed of light. In other words, this is u prime. Then what we observe here, u, is a u prime is c plus, and let's say this is almost the speed of light, all right? C plus c over 1 plus c times c over c squared is 2c over 1 plus 1, 2c over c. See, if you have a flashlight on a rocket, you have this rocket ship here going this way, almost the speed of light, and has some kind of like a headlight or something that sends out speed of light. Then you watching that, c plus c is c. And notice that if the velocity is small, then you would have u is approximately u prime plus v, because of this small speeds, then divide by c squared, like you neglect this. So that recovers what we understood to be here earlier when we did Galileo. By the way, often we see beta defined as a v over c. That's another standard definition. C6, 4 vectors. So you make a 4 vector, and we use a superscript here. When we set this up in this fashion, we put CT, and we have X, Y, and Z. And if we have a differential like that, we would have C dt, dx, dy, dz. And the convention is to then have a lowercase subscript, and then when you do that, you flip the signs on the space, although some books will flip it on the time. That's they have different conventions. And then when you take a little ds squared, what you would do is you would take this is how you would set this up, but then you would get c squared dt squared minus dx squared minus dy squared minus dz squared. So this is just formality. I mean, we know this is what's invariant. Remember, we said earlier, c squared t squared, equals x squared. So if you have it in 3 dimensions, you have x squared plus y squared plus z squared, like traveling, say, some arbitrary direction. Then if you subtract the one side from the other, you're going to get what's the invariant. So this is a formal way of setting that up. And if you look at the frame of reference where your clock is not moving, then we call that the proper time, tau. So that's in the frame that's the clock is at rest. Using this equation, you get this cool result that d tau would be equal to, well, if you have the c squared, say d tau squared, let's go ahead and do that. And then you would have here, you would have this up in there. But if I want to divide by the c squared, I would get then dt squared minus. Okay, so what would I want to do here? I want to basically factor out. I want to factor out the c squared. So let's just do that here. If this is c squared times dt squared minus here dx squared minus dy squared minus dz squared, and this is going to be, over c squared. Then if I factor out, say, a delta t, I would have c squared delta t squared. I have it 1 minus, but see, dx dt is a velocity. So this is basically velocity squared over c squared. It's like all this stuff. Because if you take, dx over dt and square it, and have dy over dt and square it, and have dz over dt and square it, you have the velocity. So you have this cool equation that if you then divide by c squared, because this is c squared d tau squared, so now the c squared, these c squareds cancel, and you get here, we'll have a 1 minus v squared over c squared. And I just wanted to show you that this time in the laboratory frame would be the proper time divided by 1 minus v squared over c squared. If I took the square root, I get the same equation I had earlier. If you recall earlier, we had the equation that the time in the lab frame is the proper time divided by this expression. This is the time dilation. So this is a kind of cool way to see the same thing. You've already seen this. You already know this to be the case. So you already know this is the case. We already know this. But I just showed you some formality with the 4 vector, how to manipulate. The length of the 4 vector is going to be the time component 1 square, minus the spatial 1 squared. Then we can define here, say let's go back to your x, this is ct, and then x, y, z. Then if we were to look at, say, a velocity, a 4 velocity, we take the derivative with respect to that special time, the proper time, which is going to be an invariant. Say that's going to be the same, like a constant. This whole thing, this ds squared is a constant from different frames of reference, and see, it is equivalent to that c squared d tau squared. So if you do that, then what you do is you replace here this d tau. I mean, here we have it. We could probably do it best way by this equation. If I take d over d tau, that's going to be equal to, if I put the d tau on the right hand, if I put that on the right hand side of dt, all right, we're going to get this kind of equation here, dt. So what we did is we took the d tau and put it on the left, so it's like d tau, and then on the right d dt. So when I have this, I can go ahead and write this here as 1 over the square root of 1 minus v squared over c squared d dt, and then now put down what my x mu is, which is a ct, and then an x, y, and a z. So if I operate on here, I'll just get c, and then here I'll get vx, Vy and Vz. So I have this cool formula that the forward velocity, this is a Greek letter mu, is equal to 1 over the square root 1 minus v squared over c squared, and I would have c, and you could just put that v as a vector and just like summarize it like in that fashion. That's kind of neat. And you know, this is like saying here's four-dimensional world, and if we look at, say, a little simplification where this is x and say this is the time axis, and you could, you put c times t if you want to, make sure all the dimensions are the same. So that's kind of why that t has this c, to put them on an equal footing in 4 dimensions. And what a lot of books will do is say if you go at 45-degree angle, that's traveling at the speed of light. So if you do that, since you can't go faster than the speed of light, because the speed of light has to be measured the same in all frames of reference, then this is the future, your future light cone, and your past light cone would be down in there. And you could have another dimension here, like maybe y, but you had to throw away z because you're using that for time. So here you can like travel away and come back. So you have a freedom in traveling. This is your v. As long as you don't travel faster than the speed of light, you can travel that v as you like, but you're forced to travel in the time dimension at the speed of light. So you must go into the future at the speed of light. But you could say, for example, be at rest, say v is 0, and then just travel straight up. So you could have v is 0, but then the speed of light would still be there for the time dimension. Then if you want the momentum, just multiply by the mass, and you got it. And remember, see, this thing here can be written as that gamma. That kind of looks kind of cool when you just replace that with that gamma. So this is gamma times mc times mv. So these are kind of neat formulas. You investigate this more in detail in modern physics, all right? But notice here, if you do the length of this 4 vector by using the same trick, then what you do is when you square things, you have the time 1 squared, and then you have a minus sign when you do the space one, because that's the what we did earlier when we looked up here. You see, we put the first one squared and then minus sign for the others. So if you do this, then you get kind of a cool formula, because if you look at this thing, this is m squared c squared 1 minus v squared over c squared. But see, this thing is 1 over the square root thing squared, and they cancel, and you get m squared c squared. You get another invariance. See, this is this nice thing about the 4 vectors, that in relativity, you get the invariance when you take the length of the 4 vector. So that's very, very important equation. Okay, C7, work and energy. You might recall from a previous class when we set up the work integral, integrating f dx, we then replaced the f with ma, Newton's law, and we played around with some chain rule tricks, and we got this to be 1/2 mv squared. And if you start from rest, you just subtract 0 and do the integral, so that this is the work done goes into kinetic energy. We would like to do the same thing with the relativistic form, and Newton's law here we can write it in more general as a change in momentum with respect to time. And then for the change in momentum, we are going to put in the relativistic momentum for P, which is mv over the square root 1 minus v squared over c squared dx. And now we're going to play around with some chain rule tricks like we did before. Notice that since this is a function of v, what I would like to do is here use the chain rule working with the derivative with respect to v, since all this has v's in it. And then for the chain rule, we'll need dv dt, so that I have the expression up here and then dx. So the chain rule, the derivative of this with respect to v, and then the derivative of v with respect to t. Now here, we want to be careful. Mathematicians would not like us to move infinitesimals around, but if we make these finite, small finite deltas for the moment, then we can move them around and have delta v and a delta x over delta t. So delta x over delta t and the delta v. And then when we go take the limit, we would have here dx dt dv, and this would be v. So you would have v dv. So let's do that. d dv mv over the square root 1 minus v squared over c squared, and then we would have v dv. Now I'm going to look at this as a function f, what's in here, and this is a function g. And I'm going to set this up as taking the derivative of the product. So here's mv over the square root 1 minus v squared over c squared times v. So this is your f, say this is your g. And using the product rule, I would take the derivative of the first one and have mv over square root 1 minus v squared over c squared times the second, which is the v, and then I would have the first function here, mv over the square root times the derivative of the second one, which is the v, that's the g. So that would be simply a 1, because see, that would be dv dv. Now what I have in the integrand, so let's look at the integrand, is this one here. This is what I have in the integrand. So I can replace the integrand with this one minus that one. You may recognize this as a variation of integration by parts, but I think it's easy to see this product rule, easier to see what's going on. So this would be the integral of d dv of this whole thing, which I'll write as mv squared, put the v with the other v, over the radical. And then I would subtract this one here, so that I have this one in the integrand. So I need to put this in for the integrand. So this would be here mv over the square root 1 minus v squared over c squared, and then dv, setting it into the integrand as the integrand. Notice that this integral can be done because you're taking a derivative and doing an integral, so that's just going to simply lift, and you're going to get this. And from 0 to v, we'll start out, at rest, like we did earlier for the classical case. Then you would get 0 at the lower limit. So this is simply going to be mv squared over the square root 1 minus v squared over c squared. Now this integral here, this one can be done. We can actually do this integral because the v is going to help us out. So let's look at this integral, and let's put the m out front, and let's put here, what we'll do is we'll put a minus sign here, and how if I leave a little bit of space, because I'm going to put something in front of that v. So just do this, and then have 1 minus v squared over c squared to the minus 1/2 power. What I want here is the derivative of what's inside here. So that would be a minus 2 over c squared times the v. Say minus 2v over c squared. So if I put the 2 there and the c squared, I gotta be careful not to change things. So if I put a 2 there, I have to divide by a 2, so it cancels. And if I'm dividing by c squared, I need to multiply by c squared, so I don't really change things. Then this integral can be done because now we simply take this 1 minus v squared over c squared and go like this is n plus 1 over n plus 1 kind of thing. So this is minus 1/2 plus 1 is then a plus 1/2, and then you divide by that. And you can check this by going with the derivative. You would pull the 1/2 down, which would cancel that 1/2, and then this would become a negative 1/2, and then you would take, use the chain rule, the derivative of what's inside, which is a minus 2v over c squared. So like that works. And then you would go from say 0 to v. But let's clean it up a little bit here before we do that. Here the 1/2 that's down here, this 1/2 will cancel this 1/2. This is 1/2 up here, and then you're dividing by 1/2. And then you would have here mc squared, put those together. And then you would have here this square root, 1 minus v squared over c squared. So that's what you would have. So by putting the v squared in, or the v in, you would have 1 minus v squared over c squared. But then when you put the 0 in, you would have mc squared. And that's at rest. See, there it is. The energy equals mc squared when the particle is, or the mass is at rest. So now we need to like put all this together. So let's say W here would be equal to this part here, mv squared over the square root 1 minus v squared over c squared. Then we would have to add this stuff from this other line, mc squared 1 minus v squared over c squared minus mc squared. Now watch this cool trick here. We're going to look at this, and let's write down this as mc squared over a little factoring. So this first term, you would want the v squared, so you have to have v squared over c squared, so the c squareds cancel, and you get this. And then here, you have the mc squared out front, but since you have this in the denominator, this would be 1 minus v squared over c squared to the first power. So when you bring this in, you have something can divide by its square root. You know, you would get the square root. And the neat thing about this is that this is equal to 1. So that means W is mc squared over the square root of 1 minus v squared over c squared, and then minus mc squared. So this is the energy. See, the energy at the function of v, the energy is mc squared over the square root of 1 minus v squared over c squared. And then when you put in 0 for the v, in other words, when v is equal to 0, you then get mc squared. This is sometimes called the rest mass. In some old books, they look at this combination, talk about the effective mass, but we won't do that. We just, m is the rest mass, and this is the energy. I think this is the safer way to go. This is your general equation. And that's very, very nice. Very nice result. The derivation of E equals mc squared. So if the mass is at rest, like say this pen, if you look at the speed of light, which is such a big number, and square it and multiply by this pen, the amount of energy equivalent is tremendous. See, when you convert, that you'll get energy in joules in the metric system, and that's an incredible amount of energy equivalent in the mass. Now, looking at this work energy theorem, when you take this expression, this is the kinetic energy you're going to gain when you do, the work. In other words, when you integrate f dx, remember we got the change in kinetic energy, and if we start with 0, then we get this. So in a sense, this kinetic energy, let's go ahead and look at this. And what I would like to do is I would like to see what this reduces to if the velocity is small. Now, if the velocity is small, we'll have mc squared 1 minus v squared over c squared to the minus 1/2 power, where we'll be able to do a Taylor series expansion. Remember, when you have 1 and you have a small quantity, say plus epsilon to the nth power, that's approximately 1 plus n epsilon. So here the epsilon is minus v squared over c squared, and the n is a minus 1/2. So when you do that, you'll have mc squared, you'll have 1. You can think of just bringing this down in there, and that's going to be a plus 1/2 v squared over c squared. Simply, combining these two together in here, your minus 1/2 times your minus v squared over c squared will get you a plus 1/2 v squared over c squared. And then we still have this minus mc squared. Notice that here we have mc squared, and then plus we'll have the 1/2 and then a mv squared, and the c squareds will cancel. And then here, these two will cancel, and look at that. That's what we expect from classical physics. The classical physics is you get 1/2 mv squared. And the relativistic formula here reduces to the classic formula when the speed is very, very low. Going slowly, very, very slow speed compared to the speed of light. That's that nice correspondence principle we talked about before, where relativity formulas reduce to classical formulas when the speeds are very, very small compared to the speed of light. C8, let's look at the 4 momentum revisited. And here's the 4 momentum. This is m, dx, d tau, and that's the gamma, mc, mv. And I just wanted to point out that when we worked this out before, we show that that's m squared c squared. All right. So what I would like to do is show you some kind of neat little relationships here. If you look at this momentum here, remember your energy was mc squared times the gamma. So that means we could write this as here energy divided by c, and this is the regular momentum. And that's a neat thing about these four vectors. If you have the four vector here, you have four dimensions. You have time, and you have, say, I'll just say r, distance. And then for the four momentum, you have energy, and the c is being used to make the units come out right. And the regular momentum, that is very, very cool. And when we did this p mu, which is the length of the vector, we got m squared c squared. But if we apply it here, remember the time one gets the plus sign and then the minus sign for the space. So you get this cool formula. And I'm very fond of this formula. In other words, e squared over c squared is p squared plus m squared c squared. In other words, put the p squared on the other side. You then get this equation, and then if you multiply by c squared, you get p squared c squared plus m squared c to the fourth, which you might want to write the m first. Either way, it doesn't really matter. But what I like about this is that there's a cool little triangle that you can look at. And here, put the mc squared, the energy, the rest energy here. This is your rest energy. And then this is your energy component that's due to motion, you see. And then this is your total energy, which is the hypotenuse, which is equal to the rest energy. If you take the square root, you have the mc squared, you have this one, Pythagorean Theorem, go square it and get that, and then square this, get that, and then that's going to be the total energy squared. So looking at this, mc squared, the rest energy, and here pc, and this is the total energy, that's that nice triangle. So when that angle goes to like 90 degrees, you're getting energy is all in the pc, and this is light. See, light travels at the speed of light, and you get this result where the energy is all pc. There's no, in fact, the rest, the mass, see, it would be zero. So in other words, we say for light, the rest mass, which is what this m is for light, is equal to 0. But then what about this equation? E equals mc squared over the square root of 1 minus v squared over c squared. Well, you want m to be 0, because when v is c, you have then 0 over 0, and that means the energy can be anything. In other words, it's undefined. And we know for light, the energy is the Planck constant times the frequency. Isn't that cool? And there, the energy we're seeing from the relativity is also equal to P times C, because it's all, the m is 0, the rest mass 0. And since the speed of light is equal to the wavelength times the frequency, you find that when the frequencies cancel, you get h is p lambda. This is really cool. You wind up with a de Broglie relation. Lambda is h over p, p is h over lambda. You wind up with the de Broglie relation for light. So there's some optics there, and the energy, can be anything, because the frequencies can be anything. The wavelengths, and are accordingly, satisfying the equation, the wave, relation here, and that all fits together. So the indeterminate form for the energy for light, due to the rest mass being 0, allows the energy equation to be h times f, which is what we know is the case for light. And later we'll see that the speed of light, which is constant in relativity, is actually, you can write it, express it as involving two constants from electricity and magnetism in the study of electromagnetic waves.